Hello everyone, I'm Yuzhou from MIT. I'm going to present our work delving into deep imbalanced regression. This is a joint work with Kaiwen, Yincong, Hao, and Dina. As we may all know, data imbalance is very common and ubiquitous in the real world. For example, here I show a real-world collected dataset, which is a very large-scale and fine-grained visual recognition dataset for places classification. If we just sort the class index according to the frequency of different categories, like from high to low, we will find that the data distribution has a long tail. As the figure shows, the majority class, such as living room, has more than 1,000 samples, but for rare class, such as the museum, it is only with around 10 samples. Such imbalanced data is actually very common and natural in the real world, regardless of datasets with different attributes, such as places, actions, spaces, and so on. Moreover, in many critical applications, like that are related to people's safety or our health, such as autonomous driving and medical diagnosis, the data are by their nature heavily imbalanced. Such an imbalanced phenomenon poses a great challenge for machine learning models and has motivated many prior techniques for addressing data imbalance. For example, previous work has proposed to generate synthetic samples for minority classes using linear interpolation of samples in the same class. Other methods also propose to do data resampling by either upsample the minority classes or downsample the majority classes. Also, loss function reweighting according to the number of samples per class are also investigated. However, current techniques for learning from imbalanced data have a problem. The solutions are only studied and designed for imbalanced classification problems. Instead, many real-world tasks can involve continuous and sometimes even infinite target values, which corresponds to the regression problem. For example, in vision applications, one often needs to infer the age of different people based on their visual appearances. Here, age is a continuous target and can be highly imbalanced across the target range. In particular, it is often very hard to collect images for the very young and very old people. Similar issues also happen in medical applications, where we would like to infer different health metrics across the patient populations, such as the heart rate, the blood pressure, and oxygen saturation. These physiological signals are also continuous and often have skewed distributions across patient populations. So, why is regression different for imbalanced data? Let's start with some intuitive examples. First, consider this imbalanced dataset. Here, the x-axis is the continuous target, which is the age of people. The y-axis is the number of samples for each age. Further, let's zoom in on two target labels, age 1 and age 2. Both of them have equal number of observations in the training data. However, given the density distribution of this imbalanced dataset, we know that age 1 is in a highly represented neighborhood, where there are many samples in its neighborhood range. In contrast, age 2 is in a weakly represented neighborhood. In this case, age 1 does not suffer from the same level of imbalance as age 2. Therefore, the first difference is that equal number of examples does not mean equal balanceness in imbalanced regression. This is because of the dependence between data samples at nearby labels. In addition, different from classification problems, in imbalanced regression, certain target values may have no data at all. This challenge also motivates the need for target extrapolation and interpolation for those regions without any data. This confirms another difference that, because of the continuity of the targets, it implies the potential for target extrapolation and interpolation. So given these differences, how should we perform imbalanced regression? The first solution we propose, called label distribution smoothing, LDS, which uses kernel density estimation to learn the effective imbalance in datasets that corresponds to continuous targets. Given an imbalanced regression dataset, we argue that the empirical label density does not capture the real imbalance. To further verify this, we show that the error distribution of a ResNet50 model trained on this data. It turns out that the error does not correlate with the empirical label density. Specifically, the test error as a function of class index has a low negative Pearson correlation with the label density distribution. Note that for regions without any data, the error could still be very small. This again confirms the intuition that equal number of samples do not mean equal balanceness in imbalanced regression. Therefore, to capture the real imbalance as seen by the model, LDS leverages the idea from kernel density estimation. It convolves a symmetric kernel with the empirical label density distribution. And this process gives us a kernel smooth label density, which accounts for the overlap in information of data samples of nearby labels. And then, the resulting effective label density distribution turns out to correlate well with the error distribution now. This demonstrates that LDS captures the real imbalance that affects regression problems. Now that when the effective label density is available, techniques for addressing class imbalance problems can be directly adapted to the imbalanced regression context. For example, a straightforward adaptation can be the cost-sensitive reweighting method, where we reweight the loss function by multiplying it by the inverse of the LDS estimated label density for each target. Okay, so moving on, we have demonstrated that the continuity in the label space is important. We are further motivated by the intuition that continuity in the target space should create a corresponding continuity in the feature space. That is, the feature statistics corresponding to the nearby targets should be close to each other. Inspired by this, we propose the second solution called feature distribution smoothing, FDS. Before introducing FDS, we first use an illustrative example to highlight the impact of data imbalance on feature statistics. We use a plain model trained on images in a real-world age dataset to infer a person's age from visual appearances. We focus on the learned feature space and visualize the feature statistics for age 0. In particular, we visualize the similarity between feature statistics. Naturally, when talking about feature statistics, we focus on the mean and the variance of the feature. Here, the upper figure shows the cosine similarity of the feature mean, and the lower figure shows the similarity of feature variance. The red bar is the anchor target, which in this case is age 0. The blue bar for a specific target refers to the similarity score between that target and the anchor. We also mark the regions with different data densities using different colors. Here, the purple refers to the many-shot region, yellow refers to the medium-shot region, and pink refers to the few-shot one. Interestingly, the figure clearly shows the problem with regions that have very few data samples, like age 0 we are interested in. Ideally, one would expect that the feature of age 0 would only have very high similarity with its nearby ages, such as age 1 and age 2. And this similarity score should gradually decrease as the age increases. However, here, the mean and variance for age 0 are showing actually very high similarity to age 40 to 60, which is not expected. This unjustified similarity is due to data imbalance. Specifically, since there are not enough images for age 0, this range thus inherits its priors from the range with the maximum amount of data. And this corresponds to the many-shot region, which is the range around age 40. Therefore, feature distribution smoothing aims to smooth the feature space using the same idea as how we do in the label space. Basically, we want to transfer the feature statistics between the nearby targets. Specifically, we have a model that maps the input data to the continuous predictions. Now, FDS is performed by first estimating the statistics of each target bin. Without loss of generality, we substitute variance with covariance to reflect also the relationship between the feature elements within Z, which is the feature vector here. Given the feature statistics, we employ again a symmetric kernel K to smooth the distribution of the feature mean and covariance over the target bins. This results in a smooth version of the statistics. Now, with both estimated and smoothed statistics, we then follow the standard whitening and recoloring procedure to calibrate the feature representation for each input sample. And the whole pipeline of FDS is integrated into deep networks by inserting a feature calibration layer after the final feature map. Finally, to obtain more stable and accurate estimation of feature statistics during training, we employ a momentum update of the running statistics across each epoch. We also highlight that FDS can be integrated with any neural network model as well as any past work on improving label imbalance. After incorporating FDS into the model, now let's go back to the previous example and see how FDS influences the feature statistics. By comparing the two figures, we can verify that the feature statistics are well calibrated. In particular, for H0 group, it shows high similarity only in its neighborhood and exhibits a gradually decreasing similarity score as target value becomes larger. Now let's move on to the experiment part. So, how do LDS and FDS perform in real-world imbalanced regression problems? To answer this question, as well as to support the practical evaluation of imbalanced regression methods, we create 5 benchmark datasets that span computer vision, natural language processing, and healthcare applications. For vision applications, we have 3 datasets. The first 2, IMDb Wiki DRR and HDB DRR, are both age estimation from single input image. We also provide the third dataset, NRU-D2 DRR, which is a dense value prediction task for depth estimation. We also construct a DRR benchmark in the NLP domain, called STSB DRR. The task is to infer a text similarity score between 2 input sentences. The score is continuous with a range from 0 to 5. Finally, in the healthcare domain, we create a benchmark called SHHS DRR. The task is to infer a general health score, SF36, which is continuously distributed between 0 and 100, with a higher score, a better health condition. Note that all these real datasets have skewed and imbalanced distribution over the continuous targets. Traditionally, people consider imbalanced regression is not intrinsically different from classification, and is just as classification with more classes. So for baseline comparisons, we choose state-of-the-art imbalanced classification methods with different strategies and directly adapt them for regression. The baseline categories include synthetic samples, error-aware losses, two-stage training, and cost-sensitive reweighting. We again highlight that a nice property about our solutions is that they can be seamlessly incorporated to augment all these methods. Here we show the representative results on each dataset. We first group different methods into 4 sections according to which basic strategies they use. The evaluation metrics considered here are the mean average error and the geometric mean error, with a lower value, a better performance. On the first row, we show the performance of the vanilla model. Within each method group, we further apply LDS, FDS, and the combination of LDS and FDS to the baseline method. As the table shows, regardless of which baseline methods we choose, using LDS and FDS can consistently boost the performance. Finally, we also report the absolute improvements over the vanilla model. The improvements are large, especially for the medium shot and future regions, where the data is very sparse. Similar observations can be also made on the remaining datasets, where LDS and FDS achieve remarkable performance over all tested regions. For a full set of results, please refer to our paper. Finally, in real-world imbalanced regression tasks, certain target values can have no data at all. Here, we take a closer look at this issue and analyze the ability of our solutions for target extrapolation and interpolation. We create a subset which has no training data in certain region, but evaluate on the original test set for zero-shot generalization analysis. We show the quantitative results on the regions with training data, as well as regions that need interpolation and extrapolation. The results again confirm the superior performance, especially for the regions that need interpolation and extrapolation, where our solutions can lead to larger improvements. To conclude my talk, we proposed a new task termed Deep Imbalanced Regression. To tackle the practical imbalanced regression problems, we also proposed 2 simple and effective techniques, LDS and FDS. Finally, we created 5 new datasets for imbalanced regression to facilitate future research. Please also check out our code, data, and paper. Thank you for listening.